Welcome back, Neutron Tech crew. Today we're stepping into the world of NASAT Channel, genuinely one of the most inventive corners of the internet right now. What's happening in front of us is a deliberate choice. This amphibious vehicle starts life as a single floating hull, shaped from stacked foam panels. Before a single wheel is sourced or a motor is considered, the builder is already telling you exactly what matters most. Buoyancy comes first. That's the rule with any amphibious build. Flotation isn't optional, and tackling the hull before anything else is the right way to sequence this kind of engineering. Foam like this earns its place in DIY marine projects because it's remarkably strong without being heavy, a combination that's hard to beat. Fiberglass cloth goes straight over the foam, resin follows, and what you're left with is a rigid composite structure that's a completely different animal from where it started. At this stage, the hull is solid enough to carry everything that comes next: motors, batteries, drivetrain components, all of it. From here, the focus turns to cutting access openings into that freshly built fiberglass shell. Each rectangular aperture gets carefully marked out first, then opened up with cutting and grinding tools until the foam core underneath is exposed. Cutting into composite material, though, brings a trade-off worth understanding. Every gap you create interrupts the structural flow of the hull and opens a possible path for water to get in. The fact that each opening gets reinforced rather than left raw tells you this builder knows how composites behave under load and how to fix what cutting breaks. Attention shifts next to how this thing will actually move through water, and the answer is a hand-built water jet unit. Instead of reaching for a ready-made propeller or pump, the builder puts together a custom jet nozzle assembly using carefully layered materials. The intake is shaped with a smooth, narrowing profile that squeezes tighter as it approaches the outlet. That geometry does something specific. It trades pressure for speed, and that exchange is exactly how water jet propulsion works at its core. This is also the point where a rotating propulsion element becomes necessary to make the whole system function. Rather than buying a commercial impeller, the builder cuts and shapes one from scrap metal. A circular ring is formed to house a set of curved blades arranged evenly around a central hub. That outer ring isn't just structural, it plays a real hydrodynamic role, stopping water from escaping sideways at the blade tips and pushing the flow straight toward the outlet instead. Each blade is bent by hand, angled to grab the incoming water and spin energy into it. Precise math isn't driving these curves, but the instinct behind them is sound. Momentum transfer is clearly understood. Water arrives along the axis, picks up rotational speed from the impeller, and gets realigned by the surrounding duct as it pushes out the back. Choosing jet propulsion here isn't just preference, it shows a real grasp of what amphibious vehicles actually demand. Nothing rotates beneath the hull, which means nothing gets scraped, caught, or broken while the vehicle moves on land. Sealing is also far more straightforward than with propeller shafts, which punch through the hull from multiple directions and create multiple points of failure. When you're building something like this yourself, every seal you don't need and every moving part you can eliminate is one less thing that can let you down. With the propulsion choice locked in, attention shifts to getting the jet housing properly seated in the hull. Layers of fiberglass and resin are built up around the intake opening, one on top of another. Spreading the thrust load across a wider surface area is the goal. Without it, the junction becomes a weak spot that flexes and eventually cracks. Amphibious vehicles are deceptive in this regard. For their size and weight, the forces they generate during acceleration can be surprisingly intense. With the propulsion choice locked in, attention shifts to getting the jet housing properly seated in the hull. Layers of fiberglass and resin are built up around the intake opening, one on top of another. Spreading the thrust load across a wider surface area is the goal. Without it, the junction becomes a weak spot that flexes and eventually cracks. Amphibious vehicles are deceptive in this regard. For their size and weight, the forces they generate during acceleration can be surprisingly intense. Threaded inserts and metal fasteners are added next, drilled directly into the jet housing for a secure mechanical hold. A precisely located opening allows the rotating shaft to pass through cleanly. Alignment here isn't optional, it's everything. Zero leakage isn't the target. Controlled minimal seepage that stays manageable during use is the realistic and perfectly acceptable standard. Once the jet drive is fully locked into the hull structure, the build moves on to power transmission and control. Before anything else, the gearbox gets a thorough clean. Old grease, contaminants, and metal debris all have to go. Every internal gear and bearing is inspected, then freshly lubricated, bringing efficiency back up and cutting friction down. Next, the gearbox housing is modified and resealed, with fastener holes cleaned out and rethreaded wherever needed. Custom machined bushings and adapters then ensure the gearbox output sits in perfect concentric alignment with the impeller shaft. Looked at as a whole system, this drivetrain layout makes the project's core intention clear. Electric propulsion brings consistent torque delivery, instant throttle response, and a far simpler sealing challenge than any combustion engine would present. At the speeds this vehicle operates, torque and dependability outweigh raw power every time. The gearing ratio also plays a direct role in how efficiently the jet moves water. Get it wrong, and the impeller spins too fast, triggering cavitation that strips away thrust and wears down components. Here, the build takes its most inventive turn. A bicycle is being stripped down and worked directly into the hull structure. That's a considered decision. Bike components bring low weight, ready-made suspension geometry, and rolling efficiency all in one package. Keeping the swing arm, axle mounts, and hub alignment intact means there's no need to engineer a ground contact system from scratch. Steel arms are welded outward from the bicycle frame, connecting it directly to the hull. Acting as structural bridges, they carry both vertical and horizontal forces from the wheel assembly into the composite body of the vehicle. That connection closes the loop. What started as a powered platform is now a fully controllable amphibious machine. Focus shifts now to steering, articulation, and how the machine communicates through movement. Every bearing, seal, and mating surface gets checked and corrected before anything goes back together, because binding is far easier to prevent than fix later. From there, the work moves to how steering is actually triggered using a mechanism that travels in a straight line. Out of threaded rod and a spring assembly, a push-pull actuator is built from scratch to handle the job. What this does is take a turning motion and convert it into a straight push or pull, which is what makes the wheel swing left or right. Concentric metal tubes, threaded rod, and bushings make up the actuator, and every joint between them is fitted with care to keep movement tight. Leave any slop in there, and you'll feel it immediately. Vague steering, wobble, and instability the moment the ground gets rough. From there, the actuator connects directly to the suspension arm, the one built from a bicycle fork. That fork already comes with the right geometry for a steering axis, which means the wheel can pivot naturally without rethinking the entire front-end layout. Connection is made through clevis-style joints, a simple but effective choice that allows angular flex while still passing linear force right through. Wherever the steering hardware meets the hull, those attachment points get another layer of fiberglass and resin. The build has now reached its final mechanical tuning stage, the part where everything gets dialed in. First up is the suspension, specifically the load-damping setup built into the steering and wheel assembly. A coil spring shock absorber is installed along the line of the steering linkage and swing arm. Then the gearbox and motor interface gets pulled apart once more for one last close look. Where needed, shafts get remachined to tighten the fit and bring everything into proper alignment. Taking something apart this many times might look like second-guessing. It isn't. First-time builds have a way of hiding problems that only surface once the system is under load or connected to something else. Shaft ends, spacers, and couplers are all brought to final tolerance through precise machining. Their job is to carry torque from the electric motor cleanly into the drivetrain. No backlash, no binding. Custom machined spacers and washers are added to the steering linkage as well, tightening things up one step further. What these pieces actually do is manage axial play at every pivot, so that when you steer, something actually moves rather than just absorbing the input as slack. Getting that tight isn't only about clean handling on land. Out on the water, it matters even more. Fluid resistance has a way of turning small oscillations into big ones, faster than you'd expect. Step back and look at those welded arms, and the thinking behind them becomes clear. Holding the wheel hub in a triangulated arrangement means vertical loads get absorbed without the structure bending, while still leaving room for controlled movement. That same triangulation is what stops the wheel from getting pushed backward the moment it hits something on land. Borrowed from motorcycle and ATV engineering, the suspension design has been adapted to work within the limits of salvage tubing and basic hand tools. After the main frame is welded together, the shock absorber gets built permanently into the suspension system. A coilover spring sits between two reinforced anchor points, free to compress as weight comes down on it. The spring rate is deliberately on the stiffer side. That's an intentional call, accounting for the vehicle's total weight and keeping it from pitching forward under load. At the platform's mounting points, layers of fiberglass and resin are being applied as a finishing step. The goal isn't purely strength, it's about distributing stress over a broader area rather than letting it concentrate in one spot. These patches work like composite washers. They stop bolts from pulling through the material and prevent cracking over time. After everything cures, the suspension arms go back on and are torqued down properly. Now that the structure is solid, focus shifts to how the suspension moves and absorbs impact. The coilover spring is fitted and dialed in, and the linkage geometry gets tested across its entire range of motion. Hydraulic integration comes next. The red high-pressure hose is cut to length and fitted with threaded couplings at each end. Routing is done with care, keeping the hose away from sharp corners and anything that runs hot. From there, it connects the actuator to the control valve, closing the steering circuit. The custom brackets earn their keep here, holding the hoses firmly so vibration can't work the fittings loose over time. After everything is connected, the system is bled until the lever responds with solid, consistent resistance. Once braking is dialed in, the handlebar controls are fitted and tensioned. Each cable is measured, cut to length, and terminated by hand, then routed in smooth curves that keep drag to a minimum. Brake lever travel is fine-tuned 1 mm at a time until the rear caliper engages progressively. No sudden grab, just a controlled steady bite. Those earlier fiberglass patches are sanded flush and feathered smoothly into the surrounding surface. A final protective layer then goes over the whole deck, sealing the fiberglass and metal underneath into one continuous waterproof shell. Skipping this step isn't an option. Any moisture getting in would put the electrical components housed inside at serious risk. Once the deck has fully cured, the suspension goes in for good. The coilover shock is bolted into its permanent position, and the linkage geometry is run through its full range, compression and rebound both, to confirm everything moves as it should. Final adjustments at the head tube complete the steering assembly. Every fitting is snugged down gradually, with alignment checked as you go, so the hoses settle into place without kinks or tension pulling at them. After that, the steering cylinder connects to the front linkage, and the hydraulic steering circuit is complete. Those thick red and blue cables aren't just for show. The color coding and gauge tell you straight away this is a high-current DC system. Cutting corners on wire size would have made routing easier, but the builder chose electrical headroom instead, protecting against voltage drop and heat buildup. Durability runs through the entire assembly, most visibly in the soldered connections used throughout. Every joint gets physically secured before any insulation goes on, which dramatically lowers the chance of a connection failing under repeated stress. Each termination is sealed on its own before the conductors are grouped, a deliberate step that keeps moisture out from the start. Worth paying close attention to is the industrial multipole switch block fitted with copper bridging elements. Rather than powering everything at once, the vehicle seems designed around selective activation. Only what's needed runs at any given moment. How the motor is installed tells you a lot about the thinking behind this build. Mounted openly on solid metal brackets rather than tucked inside a sealed enclosure, it stays fully accessible at any point. That open mounting also lets heat travel outward through conduction, into the brackets, into the structure, and eventually into the hull around it. In effect, the hull itself becomes a heat spreader, a large passive mass that absorbs and distributes thermal energy away from the motor. Running externally and kept loosely in place with zip ties rather than sealed in conduit, the wiring is fully visible by design. That choice means any circuit can be followed, tested, or swapped out without dismantling anything. What this project turns out to be isn't a rough hybrid experiment, it's a genuinely thought-through piece of engineering. Through it, we get to see how systems built for land can hold their own in water without sacrificing reliability to do it. Each major decision made here points back to one central idea. The moment this vehicle moves from ground to water, everything that was complex needs to become simple and stable. Wheels, suspension arms, steering linkages, and other exposed mechanical parts aren't just accepted as baggage once the vehicle hits water. Each one is deliberately pulled back, folded away, or locked out of action so the craft can take on a clean, hydrodynamically neutral shape. That transformation cuts drag and removes any risk of components moving unpredictably through the water. Perhaps most critically, it stops water forces from loading up on parts that were only ever designed to work under gravity. Letting those systems retract or settle into fixed positions keeps the builder well clear of a trap many others fall into. Rather than trying to waterproof every land component to a higher standard, he simply removes them from the equation. Temporary absence turns out to be the most dependable fix. Just as significant is how naturally this folding logic connects to the electrical and propulsion layout. With the mechanical systems out of the way, the motors no longer have to fight against suspension friction or wheel drag. Every bit of electrical capacity can go straight to propulsion and control, nothing wasted. That clarity reinforces a broader idea worth holding on to. Transitions are where things go wrong, and the most reliable answer to that isn't adding more, it's cutting back. He doesn't expect one setup to perform the same in both worlds. He builds for change instead. What makes this project succeed isn't any single component. It's the quiet discipline of knowing when to hold back. These folding parts aren't a showpiece or an engineering trick for its own sake.